So hello, today will be practice problems for chapter 8. Just a reminder, today being April 2nd, there is an exam 1 week from today on April 9th. The general plan is Monday, the 5th. I'm going to go through last semester's exam. Wednesday, the 7th will be a extra review session where it's going to be, I'll cover whatever the hell people want me to cover. And the 9th will be the actual exam. That's the setup. That's where we're going with. Here we go. So as I said, I'm going to start by doing problems for chapter 8 though. These problems are actually pretty spread out in material since chapter 8 is pretty spread out in material. The first one is going to be an equilibrium problem and is not an old exam problem. The second one is a torque problem in non-equilibrium, and this is part of an old exam problem. There used to be a part B and I think a C on this problem. But the part B and C came from something from chapter 7. The third one is a conservation of energy problem. This is an old exam problem that was problem 1 on the exam. And the fourth one is once again part of an old exam problem. There was other parts that came from chapter 7. I like to mix chapter 7 and 8 in exams, which you'll get to see when I do practice exam on Monday. But I'll get into it. This first problem says, Spider-Man, who has a mass of 76 kilograms, crawls onto a steel beam to retrieve a camera he left webbed to one end. The beam is uniform with a mass of 20.4 kilograms and is 6 meters long. So we have there, let's just start writing down what we have. 20.4 kilograms is the mass of the beam. 6 meters is the length of the beam. The beam is supported by a wire at the end of an angle of 60 degrees. The camera, which is at one end, has a mass of 1.27 kilograms. I'm going to call that MC for camera. There's also MS for Spider-Man. When Spider-Man moves a distance x equals 1.25 meters onto the beam, what is the tension in the cable? If I want to find a tension, tension is a force. And so I'm going to start this like any other force problem. I can say the sum of forces equals 0. But now with this chapter, we know if this thing is not moving, and it doesn't say it's moving, but we kind of assume it's not moving. Is it moving? We have something him falling or sliding. If he's just going across a beam and doesn't say otherwise, it's probably not moving. That would make equilibrium. So I could say not only is the sum of forces equal 0, but so is the sum of torques. And for either one of these, I need to start with a free body diagram. Now, there is very few people in the room, but I'm going to try this anyways. What forces are acting on this beam? If you guys are willing to unmute and tell me, what forces are acting on the beam? I saw you unmute, but didn't hear you.
I say gravity.
Gravity. And there's actually multiple gravities, because there's the gravity due to Spider-Man. There's the gravity acting on the camera. And there's also on the beam itself. Because blue, draw. Maybe I should just try typing. Because, because Spider-Man is affected by gravity, MSG. The beam itself is affected by gravity, MBG. And the camera, MCG. Now, of note, I have to say where these are applying. The weight of Spider-Man is where Spider-Man is. The weight of the camera is where the camera is. But the weight of the beam, this is a long beam. So I can just say it's right at the middle of it. What other forces are acting here?
Would tension be one?
Yep, tension, which is what we're solving for. And the tension will be right along the wire, like so. And there's actually one other force here that I'm just going to give you guys. If that was all the forces you had, this whole thing would just going to view and have the bottom drop out. This hinge right here is going to apply some force. It's just going to be up in that general direction at some weird angle. Because without that, that side would just fall down or go like flying into the wall. It's kind of like a normal force actually, but it's a little more complicated. Now, if I want to solve for tension, I could do the sum of forces. But if I do the sum of forces, this force due to the hinge, this guy right here will come into play. And I don't know what angle it's at. I don't know its magnitude. It's just meh. And so what I'm going to do is I'm going to say the logical pivot point is the hinge pivot. That this spot right here, let's switch colors, is what the whole thing would hinge around. I can make that my pivot point. And if I can make that my pivot point, I'll say in the sum of torques equals 0, each torque is all F sine theta. Well, really I should deal with the vector if it's positive or negative. And I can say the torque from the hinge, the torque from Spider-Man, the torque from the beam, the torque from the camera, the torque from the tension. And if I go through, I'll say, okay, let's start with, let's make our way left or right. The torque from the force on the hinge, this force F. Well, that's at the pivot point. For that force, it's at R equals 0. And so if I say the torque from F plus the torque from M Spider-Man G plus the torque from M beam G plus the torque from M camera G plus the torque of the tension, I'll say that this first one is 0 because it's at the pivot point. R equals 0 for it. I'll then go to Spider-Man. In my equation RF sine theta, I would say Spider-Man is a distance x. The force of Spider-Man is the mass of Spider-Man g. If left to its own devices, that guy is going down in this way. That's clockwise. We know all clockwise torques are negative. And it's at 90 degrees. It's at 90 degrees because R is flat this way and gravity is straight down. And so I just have to plug in the sine of 90. But the sine of 90 is 1. So that's my value. My next torque going down is the one for the beam. The beam, I'm going to say the torque happens halfway down it. So R is L over 2. The force is the mass of the beam G. This is also clockwise and is also at 90 degrees. My next one is the camera. The camera is at the end of the beam, has a force of mass camera G, is still clockwise, and is still at 90 degrees. And my last one is the tension. The tension is at the end of the beam. Its force is just T, I don't know what it is. And this one's not at 90 degrees. It's at some angle theta, as put there. So I have a sine theta. And for this guy, when left to its own devices, is pulling up this way. It'll swing it around. That's counterclockwise. And so this is a positive torque, where the sum of torques equals 0. Any questions there with all that? Because that's the hard part. So I want to find the tension. So what I'm going to do is I'm going to take all these negative things and add it to both sides. LT sine theta equals X MSG plus L over 2 MBG plus L MCG. And then I'll divide both sides by L sine theta. Oops. Which will allow me to plug in. L is 6 meters. I'm just going to start this again on another line because I'm not going to fit it. And I don't want to make it messy. Too late. Mass of the beam, 20.4. Mass of the camera, 1.27. And the angle, 60 degrees. And it's annoying. There's a lot of numbers there, but I'll just kind of put that all in my calculator and get a value. That's the general idea here. When doing torque problems on the homework, the first few are equilibrium problems. There's a window washer. There's a beam sitting on a platform with a rope holding it up. There's a few. Just make a pivot point, do the sum of torques around that point, and go and RF sine theta each piece one by one. Keep track of its clockwise or counterclockwise. Any questions? Now this assumed equilibrium conditions. Hold on a second. I gotta see my. Nope, my headphones are still charging. This assumed equilibrium conditions. This assumed there was no angular acceleration. And this next problem, which is part of an old exam problem, does not do that assumption. It says Okoye, the head of the Dora Milaje. So I read comics and I've seen the movies 5 million times, but the comic thing goes in my mind. So I never know exactly how to pronounce these things because it's my mind pronunciation only. But Okoye, the head of the Dora Milaje from Black Panther, wields a spear with a mass of 8.07 kilograms. The 1.73 meter, let's just start writing. Mass equals 8.07 kilograms. The spear that's 1.73 meters long is initially at rest. It's initially not moving. When she starts to spin it around the center, labeled O in this picture, using both hands. One hand applies a force F1 of 6.52 newtons at a distance of 0.045 meters from the center. The other hand applies a force F2 of 5.23 newtons, a distance of 0.2 meters from the center. Both forces are perpendicular to the spear as shown below. That means theta 1 equals theta 2 equals 90. What is the angular acceleration of the spear? Now, if I want to do this one, as I said, this is still torques. I'm still going to say we can do torque, where torque is RF sine theta. But for this, I'm going to say the sum of torques is not 0. It's I alpha. And then if I want to get the angular acceleration, which is alpha, I would just need to find the sum of torques. This will be a lot like the first problem we did in chapter 4, where the sum of torques would be a complicated piece of equation. And what I can say is as she spins this, I wish I wasn't wired, I'd grab something better to spin. But if she's taking this, she's pushing with one hand this way, one hand that way. She's pulling, you know what? Spill, haha. She's pushing with both one hand one way, one hand the other way, and applying a force in either direction. A force in either direction that will make it spin. Now, when I look at these forces, you kind of would instantly think they're in opposite directions because one point's up and to the left, one point's down and to the right. But when torque-wise, they're not. F2 is pushing it in this direction. F1 is pushing it in that direction. Both forces are giving a clockwise torque. That means the sum of torques is just going to be torque 1 plus torque 2. Well, they're both in the same direction because they're both going clockwise. And for each torque, I would just say torque is RF sine theta. Torque 1 will be R1 F1 sine theta 1, but it's 90 degrees. The sine of 90 is 1, it goes away. Torque 2 is R2 F2 sine theta 2, but the same logic. This equals I alpha. Now keep in mind, meanwhile, this I'm not going to bother writing it down. I is 1/12 ml squared. Well, actually, before I even do that, I'm going to just take this. I'm solving for alpha. I'm going to divide both sides by I and say alpha equals R1 F1 plus R2 F2 over I. Well, as I just said, that is R1 F1 plus R2 F2 over 1/12 ml squared. Or 0.045 meters times 6.52 newtons plus 0.2 meters times 5.23 newtons over 1/12 ml squared. And that's the idea. If you have multiple torques, you just do the sum of torques. And instead of right minus left, up minus down, it'll just be counterclockwise minus clockwise. And everything is counterclockwise, so they just add up. And I would say the sum of those torques equals I alpha. Now, as I said, when this was on an exam, it had a part B. The part B said using that alpha, use kinematics. That's how this whole came at rest comes into play. It was a lot like the problem we did in class with Goku. I mean, it kind of looks the same too, except it didn't get into angular momentum. It went into something else. I don't remember what. It's been a few years. Any questions on this problem? Now, this chapter had three main topics: torques, energy, momentum. And I'm going to do this as four problems: torque, equilibrium, torque, not equilibrium, but then energy and momentum. So let's look at an energy problem. Now, most of the time, in terms of your upcoming exam, any energy problems normally come up as problem 1, because the first problem will be conservation of energy. And unlike in chapter 5 when we had conservation of energy, really like chapter 5, we're going to use the same logic as we had in chapter 5. It's just now we have rotational energy. And what this problem says is, in the very early original Donkey Kong game, it's the first game with Mario in it before, Super Mario Brothers, although he was called Jumpman. Donkey Kong rolls barrels down a ramp at Mario, who tries to jump over them to save Pauline. If Donkey Kong places a barrel at top of a ramp and lets go, what that means, if he's placing a barrel, that means right here at the top, we have no velocity. If he places a barrel, let's go, what is the linear velocity of the barrel at the bottom of the ramp? So we're saying here, what is V bottom? And it says the top of the ramp is 1.3 meters above the bottom of the ramp. So I'm going to say my height here is 0, and my height here is 1.3 meters. If I want to solve this, I have something changing height, and due to a change in height, changing velocity. That is conservation of energy. What I can say is my energy at top equals my energy at the bottom. Well, energy is just going to be a combination of kinetic plus potential. My total energy is just going to be this plus this. But here's the thing here. This problem does not have a spring. There's no springs here. And this 1/2 kx squared term is only for springs. Being that there's no springs, I'm going to get rid of that term and say it doesn't come into play here. There's no springs. I don't need it. And so my energy at each point will be a combination of linear kinetic plus rotational kinetic plus potential. Now at the top, it's not moving. So at the top, it has just potential. It has a ton of potential. At the bottom, it's at the bottom. It no longer has any potential. It has just kinetic. And so there's my equation for energy at top and the energy at the bottom. But here's the thing. I'm solving for V, but I got this omega term. And omega is angular velocity. But like we covered in class, if anything is rolling, when something is rolling, it's doing two things at once. It has a linear component and it's spinning. That's what rolling is. It is spinning while moving to the side. And those two bits are related. They're related as V equals omega O, or rearranging, omega equals V over O. I also know that it's a cylinder. And for a cylinder, the moment of inertia is given as 1/2 mr squared. And what I'm going to do is I'm going to take this equation. Oh, I switched pens by mistake. Though it looks basically the same on the screen anyways, but doesn't look the same to me, so I'm going to switch back. I'll just take this equation and say, okay, 1/2 mv squared plus 1/2, and I have this I. But I have an equation for I. I is 1/2 mr squared. And then I have omega squared. But I have an equation for omega. Omega is V over O. And I'll just plug them right in. You see, I can't solve for them. I don't know M, I don't know O. So if I try to use these numerically, I'm not going to get anywhere. I don't have enough terms. But if I just go and plug in the equations, I can simplify this top line. It's 1/2 mv squared plus a half times a half is a quarter. Mo squared v squared over O squared. Some O squareds cancel out there. 1/2 mv squared plus 1/4 mv squared. And I'm going to add it up ahead of time this time. A half plus a quarter is 3/4. And so my energy at the bottom, instead of saying 1/2 mv squared plus 1/2 I omega squared, I can just say it's 3/4 mv squared. And since my energy at the top equals my energy at the bottom, that means my energy at the top equals my energy at the bottom. You know, without me doing this, that's a really dumb sentence. Because my energy at the top equals my energy at the bottom, that means my energy at the top equals my energy at the bottom. I'm fully aware of how stupid of things I say, but it kind of makes sense when I'm writing it like that. I'll divide both sides by m, multiply both sides by 4, divide both sides by 3, and then square root. Well, I can plug in. What's y? 1.3 meters. Questions? Does this make sense? Okay. The last problem I'm going to do today is going to be conservation of angular momentum. Conservation of angular momentum comes in a lot of different ways, but normally the way you see it show up is someone spinning something and they change its radius or its mass if it's fancy, and that changes its speed. Any problem that has a change in speed due to a change in mass or radius, that's conservation of angular momentum. And this problem is about old school God of War. It's actually, this problem's older than the new God of War game, although it kind of still works. And it says Kratos from the God of War video game series fights with blades attached to chains. Let's say Kratos is spinning one of his weapons like this, vertically, with a radius of motion of 1.22 meters. He spins the blade, which has a mass with an angular speed of that. He then lets out more chain. So it's suddenly let's start smaller. So he's spinning it like this, and then he lets out more chain. When he lets out more chain, he increases the radius. Applying no other torques, what's the new angular velocity after he lets out more chain? See, what we have here is something changing radius. And because it's changing radius, changing angular velocity. That is conservation of angular momentum. Anytime you are changing radius or mass and cause a change in speed, what we'll say is initial angular momentum equals final angular momentum, where angular momentum is I times omega. Now, this one is another one that is part of a problem on an exam. This was actually part C. The earlier parts, I think it was something to do with centripetal acceleration from chapter 7. But what I can say here is he is spinning this around with a radius of 1.22 meters. And he is spinning it with a speed of 125 revolutions per minute. Okay, I'm going to stop right there. And revolutions per minute, I never want to use. I do happen to know, though, that one revolution is 2 pi radians. And 1 minute is 60 seconds. And so if I want to convert revolutions per minute to radians per second, I'm just going to multiply by 2 pi, divide by 60. And then I say, he lets out more chain. The radius becomes 1.89 meters. What's the new angular velocity? And so just like I highlighted on the screen, L initial equals L final. I initial omega initial equals I final omega final. Now, as for I said what I is. I said treat it like a point mass. And the moment of inertia is mr squared. Now, the mass isn't changing here. But if I equals mr squared, that means it's going to be m all initial squared omega initial equals m all final squared omega final. M isn't changing here, so I can cancel it out. I'll just divide both sides by m. And if I want to get omega final, like how I went 1 initial, 2 final, let's be consistent. This says all initial, all final. I'm sorry, I switched my format as I wrote it. If I want omega final, I'll just divide both sides by all final squared. All initial squared, omega initial, over all final squared. And say it's 1.22 meters squared times 13.09 radians per second over 1.89 meters squared. And there's my value. It goes slower. It goes slower because it has a bigger radius. It goes slower because it has a bigger moment of inertia. And that angular momentum is conserved. That's the idea. Any questions?
I feel like these angular momentum ones are so much easier than the first other problems.
They can be. Normally it's, as I said, this can be part of a problem. I can't give 25 points for this. So like this one, I happen to remember the first part was what is the tension of the chain at the highest point, and you had to do with centripetal acceleration. But yeah, they can be. Because it's pretty straightforward. The one on the homework, if I remember correctly, has something changing mass, but it's otherwise the same idea. The one on the upcoming exam, I'm not going to tell you if it's there. Whether or not we do conservation of angular momentum or what it is. I did write the exam. I wrote it last week. Yeah, I wrote it last week. Okay. So we're going to stop there. Have a good weekend. Monday, I'll start review. And yeah, bye.